So we stopped here. Okay. Well, those who are already familiar with linear systems, we know what we can do with this, right? We can find the eigenvalues of this, we can find eigenvectors, right? And you know how to infer the stability of the system, of the linear system using the eigenvalues, right? We'll just pause for a while, okay? And we'll make the notion of a dynamical system more formal, right? So because we'll need that notions like the flow associated with a dynamical system and what is that vector field that I talked about, right? So we'll do that and then we'll come back to this thing, right? And yeah, so we're going to take a pause from this, right? So our next topic is dynamical systems, flows and vector field. So a dynamical system is a is assigning, or maybe I will give a more rule that describes the evolution of maybe I'll make it more rigorous definition. An evolution rule, okay, an evolution rule, okay. So this is a very little, again, a crude definition. A dynamical system is it's an evolution. It assigns it's an evolution rule that describes the motion of a trajectory as a function of one parameter. Think of time in state space, right? So we'll make it again, this is not very formal definition, we'll make it more formal, right? So more formally, we need the following, right? So let D be some domain. Domain means open and connected set. If you are not familiar with this, don't worry too much about this. It all says open, we have said, we have seen open ball. Connected means it's in one piece, okay? And yeah, let D be a domain in Rn, okay? So I'll give more, yeah. A dynamical system on D is a triple what does this triple consist of? It consists of this D, then this half interval, right, and map phi, right, such that it satisfies the following properties. Okay. So there are three things. There's a set here, which is a domain, and then there's a half interval, open interval, and then there's a map, right? So what is this map? It takes one element from this Cartesian D and gives you an element back in D, right? So now we have all the ingredients. So this is a map. That means I have to define what is this map, right? The map is defined from 0 infinity Cartesian D to D, right? D is a open and connected set, and this is just a half interval, right? So the following, in fact, not properties, axioms hold. So the first is known as the continuity. So you denote this map by phi, will parameters as phi tx. Okay, t belongs to 0 to infinity. So think of t as some time, but it need not be time. It's just a parameter. It's just a one parameter. But for all our dynamical system, you can think it as time, right? And x belongs to this d, right? Think of d as some subset of a state space, right? So for a fixed x in d, right? So fixed x is okay. This is continuous. That means if you fix the x, it is continuous as a function of time t, right? And for a fixed t in 0 infinity, phi of tx is continuously differentiable, right? That means C1. Continuously differentiable means derivative exists and is continuous, right? We denote such functions as C1. Okay, 1 means once differentiable and it is continuous, right? So you need this. The first requirement is the phi has to be continuous in t and continuously differentiable in x. Okay. The second property is consistency. So phi at 0 and you supply any x, maybe x naught, right, or can be any x, is nothing but x itself. That means you just stay there itself, right? If t is 0, right, and you apply phi on this, you will remain at x itself. Okay, so think of this as like a initial condition, right? And the third property is the what is known as the group property, which is a most important property, or the axiom. Okay, so what it says is phi of t some x, phi of tau, sorry, phi of remember what is this map? You supply an x and t, it will give you a point in D, right? This is still in D, right? And this is in the 0 infinity interval, right? So again, this is again another flow, right? So what it says is that you start with x, right? Then evolve up to tau time, you go and stop somewhere in D, and then you treat that as the initial point and you evolve for time t, right? And then you will stop at some other point in D, right? So this is same as you simply add up the times and act it on the point, right? This is for true for all tau t 0 infinity, and so this is known as the group property. This is the most it captures the true nature of this flow, okay, because these are more of regularity thing, continuity. This is about the initial condition, okay. So this is a group property, okay. So a dynamical system, you see, I don't talk about differential equation or anything. This is my dynamical system given by the triple. 3 ingredients: a state space thing, interval for the one, that parameter t, right, and a map, okay. Now let me give you some interpretation of this flow, okay, why that word flow comes. So this flow is a map from, we have seen, 0 infinity Cartesian d to d, okay. Now say fix t in 0 infinity, okay. You fix t, that means you allow only the x to vary, right. So what happens? So you have some d, okay, you have d, and this is also d, right, and you have this map phi, right. So now it acts on a set now because t has been frozen, okay. So now phi acts on d and gives you again a d, right. So what it does is you supply some initial set d naught, a subset of d, right. This gets mapped to phi of, okay. So this is some set, this is also some set, right. So think of flow, fluid flow, right. There's a volume of liquid, right, and you have frozen time, say take t is some 10 seconds, and you see what happens to that volume of flow, right, at the end of t, some time t, right. So this captures, for a fixed t, it captures the usual sense of fluid flow, right, and this is not a point, this is a set, right. So think of this as of some volume, right, and which has flowed over a period of time t, okay. The other way is now fix x in d, right. So this map, when you do this fix, we'll denote it by phi t now, right, with a subscript. So this is a map now from d to d because you have frozen t, right. And now you fix x, what happens? So you have d, right. Now x is fixed, that means it's a point, right, and you are allowed t to vary now. So what you get? You just get some curve, right, as t was, right, you get some curve which gets maps to d. Of course, this picture is little, and I should not use this d separately, this d, it is the same, right. So I use this to show that, you know, it's a flow, it's a volume flow, right, but this picture I can very well just use 1d, right. You start with some point because this is fixed, and then you are allowing t to evolve. You just get some curve in t, right. As t evolves, this curve also evolves, right. And this curve is, we have given the requirement, it is continuously different. It's a smooth curve, okay. So we call this, so we'll denote this by this map by, so phi superscript x. Now this is a map from to d because you have fixed d, right. So t, this is hungry on t and gives you a point in the state space, right. what does that remind you of? It's a trajectory or a solution, right, that you are familiar. So this is nothing but a trajectory, right? Because trajectory means time comes into picture. You're seeing the evolution of that points as a function of time t, right? So that is the nothing but the trajectory of the system. So you see, now we have made the notion of trajectory more formal, right? So now you appreciate that why the word flow is used for that. So it comes from, motivated from fluid mechanics, right? Maybe Umesh can talk more about that a little later. This flow map, okay, has some nice properties, but before that we need some math stuff. Any questions here so far? So you see, this is quite an abstract definition of a dynamical system, right? So it just requires three quantities: the d, the interval for the parameter t, right, and the flow map, right, which should have satisfied those axioms 1, 2, and 3, right? If you have that, this is called a dynamical system. Okay. So we'll be using this notion of flow heavily in this course. Yeah, so I need a notion of homeomorphism. What is this homeomorphism? Well, some of you might have heard of isomorphism, right? In linear algebra, we say two vector spaces are isomorphic if they are bijective, right? Linear and bijective, or you require linearity plus bijective, right? Or what is it? But I know it's at least you need it to be a bijective, right? So there's a notion of, that means what does that isomorphism capture? Well, if you show that two vector spaces are isomorphic, right, then you can just, you know, they are same. They are in that sense, right? So you can apply all the, you know, whatever theorems that you have for that vector space, right? You can apply, because they are same in the sense, you know, because there is a bijection between these two. Now I have a vector space, but now I have functions on that, right? These are not vectors now, they are functions now. Now, so what can I talk about functions on a vector space, right? So let H be a mapping from say some D. So this map is said to be a homeomorphism. H is said to be a homeomorphism if both H and H inverse are continuous. Okay, so that is the function and its inverse. Okay, please don't confuse this as the by inverse means it's not the reciprocal, like if I have f of x, don't confuse this f inverse as 1 by x, right? It is the inverse image, right? The inverse image, right? So H is said to be a homeomorphism if both H and H inverse are continuous. That means like this also it is continuous, and the other way also it is continuous, right? So it's more than continuity, because you are requiring H inverse also to be continuous, right? So once you have a homeomorphism, what happens is, if you take an open set here, it maps to an open set here, which is not true if it was not a homeomorphism, because if you just have continuity, only the inverse image of an open set is open here, right? It's not like this. So what I want to say is, suppose if you had G which is just continuous, okay, then you have some open set here, right? It is not true that if this is an open set and you map it through G, what you get here is an open set. This is not true, okay? But the other way is true. If G is continuous, right? So this is not true, but what is true is inverse image of an open set will be an open set here, right? If G is continuous. But now if you have a homeomorphism, since H is continuous, open set here will get mapped to open set, and because H inverse is also continuous, an open set here also will get mapped to, right? So H inverse carries open sets to open sets, right? So obviously it's much stronger than continuity, okay? Yeah. So once you have this notion of homeomorphism, then we have the theorem, okay, which captures all the nice properties of the flow. It says that it's a homeomorphism, then it's continuous, its inverse exists. That means the inverse of this map. Okay, so this is continuous. Its inverse is also continuous, right? So that means it's a homeomorphism, and then it's sorry, I missed here. Yeah, a bijective. I missed this. Right. So it has to be bijective. That means it has to be 1-to-1 onto H also has to be continuous, and H inverse also has to be continuous. Then it qualifies it to be a homeomorphism, right? So I missed out that. So we'll show that this map is a homeomorphism, right? Moreover, we'll also show that it has some nice group properties. The theorem. Okay. So what does this theorem says? That for a fixed t, the flow phi t, which is a map from D to D, right? We saw that for a fixed t, right? We gave a geometric interpretation of a fluid flow, right? So the flow phi t generates a one parameter. So that one parameter refers to this t, right? So it's a one parameter group of homeomorphism, right? And is also a commutative group under the operation of composition of flows, right? So there are two things to this theorem. One is to show that phi of t is a homeomorphism, okay? And so that means you have to show that it is continuous, which is already holds by the axiom. We have to show its inverse exists, its inverse is continuous, it's bijective, that means it is 1-to-1 and onto, right? And then the second part is that the set, okay, consisting of this flow, right, under the operation of composition of flows forms a commutative group, right? So whenever you have a group, you need two things, a set and an operation, right? For example, a set of real numbers under the addition, right? It's a group, right? So here we'll show that the set is collection of flows and the operation is the composition of flows. Okay, I'll not do the full proof. I'll just give a little bit of gist which captures the group property, the axiom 3, how that helps you in the proof. Okay, so so let us see some of the aspects of the proof. So as I said, actually the proof is very easy, right? All that you need to is just write it down. So let me first show that phi of t is a homeomorphism. Okay, to show that, you need to show that phi t is continuous, which is already true because it's axiom 1 of the flow, right? So this is done, right? Second is, we need to show that it is a bijection, right? So phi t is 1 to 1 and onto, which I will show. Then you have to show that this exists and is continuous. In fact, we don't say this. We'll write down what is this phi t inverse. Okay, so, and we show that it is continuous. So if you show all this, it means that it is a homeomorphism, because I have a bijection and both the forward map and the inverse map are continuous, right? So let me show at least this 1 to 1 and onto. Okay, I'm not going to do the full proof because of the time limitation. So what do you do? So let x, y belong to D, right? So phi t x equal to phi t y, right? To show 1 to 1, what do I need to show? X equal to y, right? So consider phi t of x, right? Okay, before that I need this inverse. So let me cite, take a little deviation. So what is this phi t inverse, right? Yeah, so consider phi t, okay, acting on I replace t by minus t. Okay, what is this? By the group property of the flow, right? It just adds up this. And by the consistency condition, this is nothing but x, right? So that means this phi minus t is the inverse of phi t. So you just take negative time, right? That's how you get the inverse of this map. Okay. So coming back to this proof to show 1 to 1, so phi t of x can be written as phi t, right? So so I can write x as I can write okay, or let me do it like this. So I just have to use the group property. Okay, so I have this, so I do just a small trick to this. Yeah, this is the trick. So right, x can be written as with t equal to 0 because this is just the consistent condition. So this I can write it as right, minus t plus t, right? This is nothing but phi of t equal to phi t of x equal to phi t of y, right? So this I'll replace it by y, right? But again by the group property, this is y, because this is minus t plus t acting on y, which is y. So you got x equal to y, right? Now let us do the this is 1 to 1, so which implies phi is 1 to 1. So let us show it is a bijection. I mean, we have to show it is onto. Okay. So how do you show onto? So you have some space here, right? This is some d mapping to d. You take a point z. You have to find some x such that phi t of x is z, right? So let z belongs to d, right? Then z can be written as phi of minus t, phi of t z, okay? Yeah, so or I can do t, okay, and I will define this as some x. So this will be phi t of x. That's all, right? So given z, I came up with an x such that phi t of x equal to z, right? So some x, right, and that x is nothing but phi minus t of z. Okay, so you define this as the point x, then phi t of x is, so you're showing that z is equal to phi t of x. So that shows the onto-ness, right? So that shows it is a bijection, right? We have shown it is a bijection. We have shown the inverse. How does it look, right? The inverse of this map is just you replace t by minus t. You need to show continuity of phi inverse, right? So how do you show continuity? How do you show continuity of a map? Either you use the epsilon delta definition or you take a sequence. So if you want to show a function is, say, some R to R is continuous, you take a sequence, right, in R such that xn converges to x, right? Then show that right, that will prove that f is continuous, right? So precisely like this, using the again the group property, try to show that phi inverse is also continuous, right? You just need to play around with this definition and the group property. Okay, so I'll not do that. I'll leave it as an exercise for you, right? So that completes the first part of the theorem, that the phi t is a homeomorphism. Okay, let us show the group properties. So we are going to show that phi t under the composition operation, right, is a commutative group. Right. So well, composition of flows will give another flow, right? Because what is it doing? you have a flow, you start from x, right? You will go to some point, you, right? Sorry, this is phi t. Okay, this is for the, yeah, this is a flow, this is not a trajectory. Yeah, so right, yeah, I mean that's fine. So you take some set d naught, right, and then you evolve for time t seconds, the whole mass moves this way, right, and then you evolve for some other time tau, right, you get this set, which is same as going from here to here by, we saw this, right. So the first group property is phi t composed with phi tau, okay, is same as phi tau composed with phi t for all t tau. Okay, it follows from the definition itself. Then, so this is the closure. Then you can easily verify that it is associative also. Okay, and then what is the group identity here? The identity element P0, right, is the identity element, because it will leave the point x invariant. That means if you apply x on it, it will give you x, right? What is the inverse? Phi minus t is the inverse of phi t, because if you apply on this, right, you get the identity map, right? And now the most interesting property is the commutative. Okay, so the fifth property is phi of t, right, composed with phi of tau, right, is same as phi as tau composed with phi of t. Why? Well, what is this? Phi of t composed with phi of tau, some acting on point, is nothing but phi of t plus tau acting on x. I now use the commutative property of the addition of numbers, right? The R real line with the operation of addition is a commutative group, right? Because a plus b is same as b plus a, right? So I use the property that the group consisting of real numbers under the operation of addition is a commutative group. So this is right. So that proves that it's a commutative group. Okay. So you see that all the proofs heavily use the group property of the flow, right? Very important property. Now from here we will now go to differential equation, right? So because this was the triple gave, so the triple G, which is given by D and what was that, phi, right, defines a dynamical system. Okay, to give you an example, our usual linear system, x dot is equal to ax, right? Say x is in Rn. So what will be the G here? G will be the state space, D is the state space, which is Rn itself, right? The interval of time is, say, we are concerned with, say, forward in time, right, 0 to infinity. What will be the phi? You supply some point, how do you go to the next point? What is that map? Through the exponential t. Exponential of t x, right? If you supply, if t is 0, you will get the initial condition, right? But if initial condition is non-zero and some t is non-zero, you you flow, right? This is nothing but the solution of this differential equation, right? So this is the dynamical system for the linear system. And you can check that indeed it satisfies all these properties, that this map is a homeomorphism, it's a commutative group under the composition of flows, right? You see that nice properties of the matrix exponential, right? When you talk about the state transition matrix, right? So all that comes because of this, that this is indeed a dynamical system, right? Right. Now, yeah, so the triple defines a dynamical system. Therefore, for all t in 0, infinity, and for all x in D, right, the triple, right, describes the evolution of the states in D, right? You allow t to vary, you allow x to vary in D. This triple will tell you how they evolve, right? Depending upon that map phi, it will tell you how given the point x and you give some time t, it will tell you where it will go, right? So that means it defines a differential equation, right? And what is the differential equation? So this x dot, this will tell you the evolution of the state. X dot is nothing but d by dt, and it is given by the d by dt of this flow evaluated at t equal to 0. So that differential equation is precisely given by this relation x dot is equal to d by dt of the flow, and we know we can differentiate this, right, because it is differentiable in t. But what did we assume? We assume only continuity in t. We assumed only continuity in t. So we require a differentiability in t. Yeah, we have to be a little careful here. Okay. Anyway, so we'll see that, right? So this is called my vector field F. Okay. In fact, yeah, maybe even I can, for the time being, remove this and write everything in the language of flow. Okay. Now you simply call x of t as phi of tx. And what do you get? Our familiar differential equation, x dot is equal to d by d. You get, yeah, so x dot is equal to d by dt of this flow evaluated at t equal to 0. You get here with initial condition some x naught, right? So the flow is nothing but the solution of your, for a given point, if you fix that point, right, the flow is nothing but solution of the differential equation, right? That's all we wanted to say that. Okay, we came it in a little roundabout way, but we wanted a more abstract definition of a dynamical system, but we also wanted to connect to a differential equation that we all are familiar, and this is precisely how you get this differential equation. Moreover, this F so you have this differential equation, x dot is equal to f of x. We call this F as the vector field associated with this differential equation. Okay, so what does that do? What is this vector field now? Okay, so the vector field, it is hungry on x and gives you a vector in Rn, right? So at a point x in Rn, f of x gives a tangent vector. It gives you a tangent vector. So what does your differential equation give you? If you supply a point x, it will give you a vector, tangent, we call it as a tangent vector, right? So the picture will be something like this. Say in a plane, right? You take some point x, right? You will get a tangent vector. This is nothing but f evaluated at some x. You give me some other point, I'll get some other tangent vector. And by the uniqueness of the solution of the differential equation, those vectors don't intersect. Okay. Now we have a dynamical system. We did linearization, right? And we also defined the notion of a tangent vector and flow, right? Next exercise is to get some picture out of that linearized model. Okay, because we cannot solve the nonlinear system, but we can do linearization, right? And then locally around that equilibrium point get a picture of the system. What do I mean by picture? I would like to see how the flow, okay, how the flow looks if you supply some point, how does it look in the vicinity of the equilibrium point, right? That is the next thing that we'll do. So before I do that, I will define a notion which is very fundamental to control, okay? The whole of control system lies on this one definition, right? If you understand this definition, which is very easy to understand, you will understand the whole of control theory. It is a big claim that I want to make, okay, but you will see that it is true, okay? And what is that, okay? You have a differential equation, okay? I will sometimes use dynamical system, differential equation, model, or whatever it is, right? So you have some set, right? So let me call it as some S, which is a subset of Rn, right? So definition, the set S is said to be positively invariant if x naught belongs to S implies x of t also belongs to S for all t greater than or equal to 0. This is a definition, and you can see that this appears everywhere, right? So the whole of you work in sliding mode control, you work in stability, okay, you work in adaptive control or whatever you want to I mean the terminology. This is at the heart of control theory, right? What does it say? That you have a dynamical system and you have a solution to this, some x of t, right? Of course, we are not computing the solution, right? This is just a definition, right? Suppose if you know that there is a solution and you are able to find this x of t, then we say that a set S, somebody has given you a set, this subset, right, is said to be positively invariant. The word positive, because we talk about positive time t, right? You can talk about negative time also, but we are interested in positive time, right? So it's said to be positively invariant. The word invariant comes because what it says is if you start an initial condition in the set S, you will remain, the trajectories will remain trapped in this set forever, right? So the picture will be something like this. You have an x naught, right? And then you have the trajectory, right, is trapped in this, right? So this definition is used to define, later on we'll see Lyapunov stability, right? So it is used to capture periodic solutions, everything, whatever you want to talk in control theory, right? So this is at the heart of control theory. you see any proof on stability, it will always involve a notion of invariant set. Okay. Fine. So now what is that we are going to do? We are going to connect the information that we have from the linearization to the picture of this flow in the vicinity of that equilibrium point. Okay. So what we'll do is we'll do a graphical method known as phase portrait. Okay. So I'll explain that with a simple second order system. Of course, because it's a graphical, you can't extend it beyond third order. You can do it for first order, you can do it for second. You can not on the board, but at least on a computer you can draw the third order for phase portrait, right? So let me write our dynamical system more explicitly like this. Means I want to bring in these components F1 and F2, right? So this is a second order system, nonlinear system, and you want to draw what is known as the phase portrait of the system. Okay. Probably I should maybe start with the first order. That will be more, yeah. So let me start with the first order. First order equation. Okay. So the first step is find out the equilibrium points of the system. All the equilibrium points. So how many equilibrium points it has? Only one at the origin, right? Even a scalar differential equation can have many equilibrium points. It can have continuum, it can have many isolated also, right? But here I just have so we have the real line, right? And I have this 0 sitting out here, which is an equilibrium point, right? So if you pick any point, what does this give? It gives you a vector, right? So if I pick any positive x, right, what does this whole quantity is? It's negative. So you take any point, I can draw a small arrow which captures the orientation of this vector. I'm not much interested in the magnitude of the vector, but rather the orientation of the vector, right? So this vector is nothing but, at any point here, x, it will be negative. This is negative, this side is positive direction. What about this side, right? Negative, but there is a square, right? So again this will be negative. What does this tell? Okay, it says that if you start any initial condition to the left of 0, where will it go converge? To minus infinity. If you start anything to the right of 0, it will converge to the origin. I use the word converge, but later on we'll use a much stronger notion called stability. Okay, but since I have not defined stability, let me not use it. Well, when I say converge, that means it's all in asymptotic sense, because this is all, the right hand side is all nice continuous function, right? So it will only go to the origin in an asymptotic sense, right? So these arrows are called, these are the I mean this is the plot of the vector field, right? This is a vector field, and if you supply a point, you get a vector, right? So now you give me any initial condition, okay? What is the solution to that? A solution, suppose this is my initial condition, solution to this differential equation, some x naught, right? So this is some x naught. is a smooth curve which joins all these arrows. Okay, in this first order case, all the arrows are in the same, in the same line, right? So the solution is nothing but a smooth curve which joins all these arrows, right? So that is your solution. Of course, I don't have analytical solution. Of course, in this case, it's a first order, I can get analytical solution. But when I picture this, it's a solution, but it's a graphical solution, right? Now, you do this for all initial conditions, right? And draw the solutions, right? That is called the phase portrait. But obviously, you can't draw for all initial conditions. So, what you draw is an approximate phase portrait, right? So, let us do this for a second order system. So, I have a second order system. So, what do? You take any point, start with some point, okay? And of course, you also need to write all the equilibrium points, okay? So write down all the, because that helps, okay? Obviously, your initial condition should not be on the equilibrium point, because by definition it will continue to stay there because the f's are 0 there, right? So take some non-zero equilibrium point. You need not be in the vicinity of the equilibrium point. Say this is the equilibrium point. You can do this phase portrait thing for any point in the plane. So it's a global picture, right? What you get is a global picture. But later on we'll connect the local analysis from linearization to this global picture. That is what eventually we are going to do. So this is some point x1, x2, right? So you draw a small vector which captures this f1, right? Say it is positive. So this is f1 evaluated at this point x, right? And on the vertical axis, you capture this f2. Say in this case, suppose this is f2. Okay. Again, as I said, you don't have to worry too much about the magnitude, right? Just worry about the sign of f1 and f2, right? Sign in the sense, of course, the magnitude is important. So what do? You get the resultant, right? So this resultant vector, I'll simply call it as some fr. So fr, the important thing is this angle which it makes, theta r, right? So we know this theta r is inverse tan we are interested in this angle, right? So you fix some vector length, right? But keep track of this theta. Okay, the theta is very important to us, right? So you come to this point. Okay, so you got one vector from this, starting from this x, you got the direction of the vector field starting from this point. Do the same thing for this, right? So again, treat this as the point, plug into this and get the angle. So maybe there will be maybe small change. Continue this for as long as you want your plane to be filled up with, right? Do this for many other initial conditions. So maybe I have something like this. Maybe I'll take some different quadrants. Okay. I'm just randomly drawing, but if you see that it's not all that random, there's a continuity also, right? The arrows suddenly don't change direction because there's a continuity in the vector field, right? It's not a discontinuous vector field. So when you draw this, if suddenly you get an arrow which is something like this, then you have done some error in your calculation, right? So you fill up all this, your plane with these vector fields. Okay. So this is called vector field plot. Okay. So you can use the Mathematica package to draw this. There's a command called stream plot. Okay. So you can use that command to draw this. You just supply F1 and F2, it gives you the vector field plot. Now, if you give me an initial condition, say this is my initial condition. how does the solution look? Well, the solution is a smooth curve that joins all this vector field. Okay, and the sense is you have to put the direction also, right? It starts here and it is moving like this. So this is nothing but the solution of the differential equation, right? But again, be careful when I say solution here, it's a graphical solution, right? You cannot extract an analytical expression out of this, right? But still, it's a powerful method because this gives you a global picture. Okay, so you can extend your x1, x2 axis as long as possible, and all that you have to do is take sufficiently number of points, draw the vector fields, right, and then given the initial condition, you get the phase portrait, right? So maybe you should do some exercises, problems to actually do this. Okay, take your calculator or whatever it is, do actually plot this, because this is a very powerful tool, very important to know how quickly you should be able to given a differential equation, quickly do a rough sketch and get some idea about how the trajectories are behaving, right? So it's a very, very, very important exercise to do for everyone, before you go and do the analytical tools. Okay. Well, I'll give you some example how this looks for some of the examples. Okay, so let me I think one of the complaints was I am not giving many examples, so let me. I have to give some example for the positively in this also. Yeah, maybe I'll do that first. It's a linear system, everyone agrees, right? Can anyone give me quickly what is the eigenvalues of the same matrix? I know one of them is -2, the other one, quick, anyone can give me? Okay, whatever it is, right? Can you also give me the eigenvector associated with this? So, anyway, you please do the competitive eigenvector associated with lambda equal to -2. Okay. Now, let me define the set S as okay. So this is the set S. How does it look? This is the one with the negative slope. Can anyone tell me what does this line depict? I already gave you some clues on the board. Huh? It's the eigenvector associated with this lambda equal to -2, right? So in fact, this S is nothing but span of, say if I call this as V1, there are two eigenvectors, but I'm just focusing on this one. There will be another eigenvector also, right? So we'll show that the eigenvectors are invariant, positively invariant under this flow. That means you start anywhere on this eigenvector, right? And the sense will be going towards the origin because it's negative, right? So it will be. If you don't know that, you can go to this dynamics here and get the arrow, right? For example, you take any point here, x is negative, so 2x will be negative, right? So you have negative here, and the y-axis x1 minus x2. So if I have a, so x1 is negative and x2 is negative, positive, so this whole thing will be negative, right? I am getting, I think I should get here like this. So minus, this is correct. x1 is minus x2. Okay, x1, yeah, sorry, x1 dot has to be positive. Yeah, sorry. So this resultant vector is this one, right? Which is also, you can see the eigenvalue is -2, so the trajectories will be approaching the origin, right? And for here it will be like this. So this is the eigenspace. This set is nothing but the eigenspace, right? Associated with this eigenvector, okay? And what does it mean to say it is invariant? Well, what it says is if you start on this, right, initial condition, you will continue to be on this. Okay, you start here, you will continue to be on this, and you will approach the origin. The approaching is a byproduct. The positive invariance doesn't require you to approach the origin, right? Even if it was diverging, it is still positive invariant as long as you remain on this surface, right? So eigenvectors, right? The span of eigenvectors, or that is, you call it as an eigenspace, is an invariant subspace, right? So you see the notion of invariance is there even in linear system, right? So how do we show now explicitly? Well, this is nothing but this eigenvector v1, right? Because this eigenvector v1 happens to be, if you normalize, 1 minus 1. Okay, so let us do that. So let me call this function as some h. You differentiate this along the dynamics, along the trajectories of this system, right? So d by dt of h of x is nothing but dou h by dou x, x dot. This is by chain rule. It's nothing but chain rule. Okay. So what is this? This is 1, 1. No, x2 by no, sorry, this is not what we should do. Sorry, this is not that. Please don't do this. So we want to show that S is invariant, right? Yeah. So we want to show that if you start with an initial condition in that, you will continue to remain in that, right? So what you have to do is you have to actually solve this differential equation in this case, okay? And then take an initial condition which satisfies this, and then you have to show that x1 of t equal to minus x. That will show that it is positively invariant. You can do that because you have a linear system. You can explicitly solve that, right? It's there. The solution is there in my lecture notes. You can have a look at it, right? So this is how you show, but there is a problem with this kind of thing. What is that? You need to know the solution to show this, right? That is very stringent requirement. We are doing nonlinear analysis. We started off saying that we cannot obtain a solution of the differential equation, but now you want to show a very important property, which is the positive invariance, and for which you want the solution to be known, right? We'll later on see how to do away with this, right? We'll do we'll give a indirect way of checking the positive invariance of this function. Right? I think even by differentiating this h, we should be able to do it, depending upon the quadrant. We will come back to that later. Okay. Yeah, so now you know what is meant by positively invariant set. You know, at least for linear systems, how to get, how to show that it is positively invariant, right? Now we'll try to piece together all this. Okay. So any questions in the meantime? We'll focus on second order system because we can draw. Beyond that it will become, of course beyond 3 you cannot, it is impossible to draw. We don't want to do first order because it is too simple, right? So much of the nonlinear behavior is captured by just looking at the second order system, right? So let us focus on second order systems. So when I say second order, I'll take it in that form. Also you can see that we have dropped this control, right? Because either you want to analyze the unforced system, or you already have a feedback law, you have plugged in that feedback law and you have a closed loop system which is now some function of x, right? So in either case I am okay by neglecting this u, right? So you have you want to analyze a closed loop system, well you put your feedback law. If you are not concerned with feedback, the closed loop system, but you just want to analyze the open loop system, set u equal to 0, right? So that's why we don't deal with control in our analysis. Okay, so the first is, so you do the, so let me call this as, maybe I'll write here. Okay, and the linearized system, I'll still use the same variable. Okay, it doesn't create any problem. So this is linearized equation about some operating point or equilibrium point. Okay, so maybe without loss of generality, we can even assume the origin to be the equilibrium point of interest, right? That means here I will assume that f of 0 is 0. Okay, of course we will also deal with the case where there are multiple equilibrium points, but if there is only one equilibrium point, I'll just shift it to the origin. Okay, right now, so we have several cases, right? I will simply put it into 3 main classes. And what are that? Based on the eigenvalues of A, right? So I will do some classification of the equilibrium point about which we have done the linearization based on eigenvalues. Okay. The first is when A throws up real and distinct roots, I mean eigenvalues, and satisfy okay. So if I have this, okay, then how does the phase portrait look in the vicinity of that equilibrium point, which is the origin, right? So it looks like this. So you have a positive eigenvalues, right? So, and this is your equilibrium point. So the phase portrait will look all escape out to infinity, and this is the typical portrait that you get, right. So you perturb it from here, they will all escape out, right. So you see even yeah, please be careful, this is not a one continuous curve, right. I mean this is one trajectory which is going away. If you perturb to the left, if you perturb little to the right, this is one trajectory, right. So that's why I just did not join this, okay. In this case, this equilibrium point is called unstable node. Okay, that's the classification. B will be, I mean, or the subcase of this would be when the eigenvalues are real, distinct, and both are negative. Okay, it will just the phase portrait will be just the opposite. I mean, the orientation will be just the opposite, right? So it's exactly the same thing. I will not draw too many this, but now the arrows are all pointing towards the origin, right? So in this case, the origin is called a stable node. Okay. Of course, you can have eigenvalues which are equal, and they will again fall in one of these two categories, right? I have just given you distinct, but it will be little skewed if you have a real eigenvalue, I mean equal eigenvalues. So I don't want to do that as a separate. Okay. Now you have case 3 where lambda 1 is positive, lambda 2 is negative. 1 is positive, 1 is negative, right? In the pendulum case, when you linearize about the upright equilibrium point, you will get exactly like this. No, you will not. Yeah, you will get like this. You will have a eigenvalues which are real, okay, but of opposite sign, right? So in this case, the phase portrait looks like this. In fact, yeah, so you can choose your coordinate system in such a way that the eigenvectors are nothing but the eigen or the axis here, right. So along one of the axis is one of the eigenvectors, along the other axis is the other eigenvector. You can always choose some canonical transformation, right. So in that, it will look like this. So you will have yeah. So suppose this is corresponding to lambda 1 is positive, so it will go away, right, but there is lambda 1 which is negative, so it will come to the origin. So if you start an initial condition on the x1 axis, you will reach the origin, right, but anywhere else, okay, say on the x2 axis, you will diverge, right. What about any other points? Well, the other points would be, yeah, something like this. So they will all escape out to infinity. They will blow up to infinity. So there is only one surface, a thin surface, on which if you start, your trajectories will reach the origin, right, which is exactly the eigen space associated with the lambda 2. Huh? What is that? Positive, right? So I am saying this one is associated with lambda 1. Okay. So V1 is with respect to this, and this is with respect to lambda 2. So in this case, this equilibrium point is known as saddle. There is no prefix unstable or stable because it is We will see later on it is unstable. Right? So we don't use the word unstable there, it's saddle. Right? Then the case where you have this is 1, so you have lambda is equal to some a plus or minus j omega. So it is a complex eigenvalues, right, with both a and omega, a and omega not equal to 0, right? Because if omega becomes 0, then it will boil down to this case, right? And if a becomes 0, then we have another case for that. So I want to deal with where it is having a non-zero real part and it's a complex eigenvalue, right? So in this case, by the way, all these trajectories that I have drawn, you can get an analytical expression because it is coming from a linear system. And please note that this is a portrait of what? This is a portrait of this system. Okay, so all this that I am drawing. So this is all the phase portrait of 2. Okay, this is also phase portrait of 2. About the equilibrium point, some equilibrium point about which this nonlinear system has been linearized. So please keep that in mind. Okay, so because it's coming from a linear system, you know analytical expressions for this also, right? So if you see the phase portrait, the time has been suppressed, right? The time has been separated. It's a plot of x2 versus x1, right? So you can eliminate time. You can write the solution of this, eliminate time, and write x2 as a function of x1. Okay, with just a small exercise that you can do that. Okay. Now, for the complex this, if A is positive, that means you have a eigenvalue with non-zero real part which is positive, right? Then your trajectories will be something, it will spiral. So this is positive, right? It will spiral out. You perturb it about that equilibrium point, the trajectories will spiral, right, and escape out to infinity. So in this case, this is called unstable focus. And when you have a negative, right, you have what is, so you have a stable focus. So the pendulum downward equilibrium point, if you add a viscous friction to it, it will show this behavior. In the presence of friction, eventually the pendulum will spiral down, right? I mean, if you plot that theta versus theta dot, right, you will see that phase portrait will be like this. It will spiral down and it will come to the downward equilibrium point, right? But this is with viscous friction. Okay. Without viscous friction, what happens is exactly this one. A is 0. That means the eigenvalues are on the j omega axis in the complex plane. What you will see is you start with any initial condition, right? You will get continuum of closed orbits, closed trajectories. Is this a trajectory? No. This is a trajectory. Okay, so please be careful. Whenever you draw a trajectory, you have to mark the orientation. If I had not done that, what does that represent? What does that represent? It represents a equilibrium set, right? So what is the difference between this and this? And this. Okay, this means it's an equilibrium set. That means if you start any point on this, you will remain there itself, and it's a continuum of equilibrium points. And it has the shape is it has formed some nice closed curve, right? Whereas these are not equilibrium points; these are trajectories. So for the pendulum, without friction, it corresponds to oscillations about this point, right? So you have small oscillations. These are, as the magnitude increases, this magnitude also, I mean this radius of this circles also will increase. The radius or the shape is not, we are interested, okay? There is nothing holy about that. What is holy about the whole thing is they are closed orbits, okay? So you start and it comes back to the same point, right? That is the peculiarity of this case when A is equal to 0, and we call this the center. Okay. So we almost covered all the eigenvalues possibilities, right? When they are real, distinct, when both are positive, both are negative, one is positive, one is negative. The complex case where the real part is positive, real part is negative, and real part is 0, right? So now question is, how do you connect this to a nonlinear system? That means you have done a linearization. Based on that, you did some analysis. Can you tell something about this system about that same point? Is the question. Let me repeat it. You have an equilibrium point for the nonlinear system. You want to analyze that. What happens to the trajectories if you start, say, close to that equilibrium point, right? What happens? Whether they go to the equilibrium point or they will escape to infinity. In what is the behavior? So we are interested in qualitative behavior, okay, not quantitative behavior, because quantitative we cannot solve it. So what we can do is at most do a qualitative behavior, right? So as a first step, you did linearization. You could solve it, you could draw the phase portrait, everything nice, right? But the question is, does this really represent how the trajectories behave in the vicinity of this for the nonlinear system? That is the question. Otherwise, if you cannot relate, then this exercise is a futile exercise, right? But if I can say, well, if you do this, if the trajectories look like this, then even in the nonlinear system, for the nonlinear system, around that equilibrium point, the trajectories more or less look like that. Then this tool will be a useful tool, right? And we'll see in the afternoon how we'll address that issue, right? So whether that question is true, whether we can do that, or whether we cannot do, or under what cases we can do and under what cases we cannot do that, right? So that is the whole discussion. So we'll meet in the afternoon. Okay. I think let me check if I have something left on. We have some time, so we can take some questions. Maybe Umesh, you can also join. Yeah, that is better. We'll pause here and take some questions because there's a lot of stuffing that has happened. Yeah, any questions? Please feel free to, I mean, however silly it may sound, but no question is a silly question, so everything is as important as, you know. Or something you want to relate to, something which you are working on, and you want to relate to whatever has been done here, probably you can speak also, that is also fine, right? Omega is 0 is this only, sorry, omega equal to 0 will be, yeah, will be sitting at the origin, right? So omega also 0 and a is 0 is when your eigenvalues are 0, right? So we will also call that under center only, right? Both eigenvalues are 0, but both eigenvalues are 0 will be a trivial system. The A matrix will be, it doesn't have to be 0, both I mean, but in second order how it can be? It has to be a 0 matrix because, huh? Yeah. Yeah, we will sort of, we will not call it as saddle, but it will come under this case itself. Yeah, it will be that. Yeah, yeah. So Ax equal to, so what will happen is, if you have continuum means what? Ax equal to 0, because that means you have a non-trivial null space for the A, right? But that is based on linearization. But I'll give an example. Yeah, simple. Okay. X equal to 0 is the equilibrium point. You agree, right? Now, if you do linearization, okay, the Jacobian is minus 3x square. Evaluated at x equal to 0 is 0, right? In fact, our sufficient condition for isolated thing also fails, right? Because A is or not full rank, right? I said that if A is, did I say that? No, I did not give that condition. Okay. So anyway, so it has an equilibrium point, isolated equilibrium point. Linearization, A is 0, right? The A matrix is 0. This is first order, so eigenvalue is 0, right? Now, for the linear system, what does that mean? 0, that means x is a constant. So whatever initial condition you give, it will stay at that, right? But if you look at this nonlinear system, if you draw the vector field plot, right? So anything on the positive side, right, will show what? Vector field will be here. X negative, this will be negative, 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 positive. So you see, all solutions will converge to origin, right? All solution, irrespective of what is the initial condition. Whereas your linearization is saying that the only solution is the initial condition. So you see, what he said is, it breaks down, okay? And that is what we are going to do in the afternoon. So in which cases, you cannot comment anything about the behavior of the equilibrium point of the nonlinear system based on linearization. Okay, that is what we are going to state a theorem, and then we'll talk about that, right? So this is a good example where the eigenvalue is 0. It is unstable, but okay, see, I have not still defined unstable, right? What I want to, at this moment I can say that if you perturb it, it will go away from that point. It will escape from that. No, because see, there in the saddle, there is also one subspace which is where the trajectories converge to the origin. Here, in the case of, you wanted to compare what, unstable node or no? All trajectories you perturb in any direction, they all escape out to infinity. But in saddle, there is one direction in which it doesn't escape out to infinity. So that is the difference. But later on, we'll see in our stability thing, that is unstable. This also is unstable. So that, see, this is in the x1, x2 plane, okay. So it will correspond to some, how do we interpret that? Physically. X1 and x2. I, I, I think that will be that homogenic orbit, right? You come back. So it will escape out. Okay. So what does it mean is, it doesn't mean that. So if you perturb along that direction, the pendulum will come down, right? It will make a full rotation and come and stop, right? So it has to be a very, your perturbation has to be take into account that. So, but there exists a perturbation such that it will, see, normally if you perturb it, no way it will come back, right, the physical pendulum, but this is of course without friction. So there is a perturbation for which if you perturb, it will go down, it will make full rotation and come back and stop. That will be the oscillate. So in fact, if you draw the local this direction will correspond to that the unstable, the stable the eigenvector associated with the negative eigenvalue, right? So you will have, so locally you will have this eigenspace here. So this one and this one, right? One direction is converging, the other direction is diverging. It is local. So I said linearization is a local thing. That means you can only talk in the neighborhood of that. What is happening in the neighborhood of that? That is the first level of. So we cannot get a global picture, right? The global picture is only available with the second order with phase portrait, right? So this is one thing. In addition to that, is that linearized thing also? Can you believe that? And that is what we are going to do in the afternoon. Under what cases we can believe that whatever the linearization has captured, that also holds for the nonlinear system.